I am back from church. I am ready to continue where I left off. So, to review where I've left off, I've been learning clock cycles and clock speed. I've watched a really helpful video. I think I should probably cite the videos that I use for understanding. Yeah, this one. I watched this one. This is pretty good. Referenced video. I'm gonna link it right here. Yes, sir. You did not want to see my ChatGPT history. Okay, so this was the answer key. I was in the middle of, like doing this. And yeah, I did this and then I moved on a little bit, but I think I should probably review why this is the way it is. So, is it throughput? Hold on, let me check. Alright, I'm back. Okay, I'm kind of really enjoying reading this, and I need to keep that up. Right now I'm learning about clock cycles and clock speed and how to measure performance, and we're on check myself. So here, the part that really confuses me is it literally tells you the answer though. Like, an extra network channel is added between client and server, increasing the total network throughput and reducing the delay to obtain network access. Like, isn't that just telling you the two answers? The networking software is improved. Okay, so for this one, I'm gonna ask chat. I don't know why this is not both. So I'm answering this question. I'm gonna copy this. And this one. Alright. I have to answer either throughput is improved or network is improved, or either. Answer key says, what did the answer key say? For B, it says latency. I'm assuming this is the I'm very curious what chat's gonna say here. Latency, how long a single request round trip takes. Cutting the network communication delay reduces this so response time improves. Throughput is in networking problems normally mean bandwidth or the network's capacity to carry data. Really? I thought throughput, the maximum amount of data you can move per second stays the same. So throughput does not improve. Your reason that saving could let you finish more tasks in the same interval, which can increase transactions per second. That is true if the application issues requests strictly serially. In that serialized model, the transaction rate increased transactions per second. In the systems that permit pipelining, concurrency, or where the dominant limiter is bandwidth for large transfers, reducing latency alone usually does not raise the long-term throughput. Bits per second. Isn't throughput yeah, the amount of work completed per unit time. The amount of work. Right. Requests, instructions, widget. Yeah, that's bits per second. How does that even make sense? So, what exactly is bandwidth? A range of frequencies within a band. Oh, great. Is the maximum rate of data transfer across a given path. Bro, these are so confusing. What exactly does that even mean? A bandwidth is the capacity size of the pipe, while speed is how fast the data travels. Ooh, I don't understand bandwidth. Okay. What is bandwidth? I'm just gonna... Can you explain bandwidth? I'm having trouble understanding that. Understand if you separate three concepts. Latency. Time, how long one piece of data takes to arrive. Bandwidth. Data per second. How much data per second can flow. Throughput. The actual achieved rate. How much data you actually get per second. So how am I supposed to know that this throughput actually refers to bandwidth? I guess this one, reducing the network communication delay, but not increasing throughput. Actual achieved rate. How much data you actually get per second. How much data you actually get. I thought it was how many tasks you complete in a given time. Why is it how much data? Ah, I guess in the given context, I thought it was like, I see where I misunderstood. I think I didn't pay attention to the main question, as it says the app uses both desktop client and a remote server limited by network performance. We are kind of strictly looking or focusing, or rather focusing on the network side of the application. I think, is that what it's referring to when it says limited by network part of the I don't know. It might be partially oh, exactly right. Network is the bottleneck, so you should judge each change pod affects network metrics. So in terms of network, bandwidth is the throughput. So when we are strictly talking about network, passing data from one end to another, we are talking about how much data is processed. Yeah, I mean, I don't even need to ask that. I already know. Okay. This is not true. Not true because we are only concerned with the scope of the network part of the app, which is bandwidth. Oh god, why is it capitalized? So if the my final question is that, so if the question had a larger scope, say it didn't have that limited by network performance part, would it be fair to say throughput? Wait, is it throughput? Aish. Throughput is determined by the bottleneck. Okay. Gotcha. Alright. This one is simple math. CPU performance and its factors. Users and designers often... Why is my MacBook not charging? Ooh, I am missing my background music right now. That's why. Ooh, let me try this. My charger's not working. What the hell is going on? Wait. I don't like this one. I can barely hear the fireplace here. Okay, why not? I should just like... Yeah, this one. Like this. Oh, that's so nice. Wow, that's nice. Wow, I'm gonna save this one. You know what? I'm also gonna subscribe to them. Okay. So today I'm gonna... Actually, I'm gonna try to finish 1.4. I don't know how much I have left. 32. These are examples and answers. I have to read this part. 7. Yeah, I can finish this. I'll quickly finish this. I'll try to quickly finish this today. Oh, okay. So today, my goal is to finish 1.4. If I can't, it's all right. I think this section is very important for me to fully understand before I dive into other things. So I'm going to try to understand this part.
슬슬 버릴 거부터 버리고 있어.
안 해도 돼, 이거.
재훈이는 23일.
All right. So all right, what am I doing right now? If we relate these different metrics, we could determine the effect of a design change of the performance as experienced by the user. Since we're confining ourselves to CPU performance at this point, the bottom line performance measure is CPU execution time. A simple formula relates the most basic metrics. Wait, I completely zoned out. The bottom line performance measure is CPU execution time. CPU execution time. A simple formula relates to the most basic metrics. Okay, The bottom line performance measure is CPU execution time. Simple formula relates the most basic metrics, clock cycles and clock time, to CPU time. Okay. CPU clock cycles for a program. So how many times the cycle has run while running this program times the clock cycle time. Oh no, clock cycles. How many cycles were there? So there's electrical pulses to the CPU, which is the clock cycle, and every time a clock cycle happens, we can measure that, right? Like by a clock, there's like a base clock cycle time. Excuse me. Excuse me. Why is the window open? Aye. So we have our clock cycle time, and this will be like, there was a video I watched, right? Oh no. Right here. I think this is the clock. Is this what we multiply it, or is this? Wait, is that not the right number? Clock cycle time. Wait, what was clock speed again? How many clock cycles a CPU can perform in 1 second? Oh yeah, it's not exactly clock speed. Wait, 3.95 gigahertz. That means 59 gigahertz. That means 3 billion 500 3 billion 3.95. What is that? Is that 5 billion 3 million 900,000? This is the how many cycles for a program, and the clock cycle time. What is that? What is the clock cycle time? That's just like, is that the same thing as bus speed? Is clock cycle time the same as the bus speed? Is the duration of one CPU clock tick. So it's not that. I don't know what it is then. Could it be one of the clock cycle? The time required to complete one clock cycle. Okay. It's just the time that it takes for one cycle. Because clock rate and clock cycle time are inverses, we can also look at it like this. Clock rate. Wait, this is also clock rate. So this is basically how many clock cycles for a program we have divided by the clock rate, the clock speed. I see. We get the CPU execution time. My Mac is not charging. I don't know what happening. What the heck? What is happening? Oh, there we go. Okay. As we will see in later chapters, the designer often faces a trade-off between the number of clock cycles needed for a program and the length of each cycle. Many techniques that decrease the number of clock cycles may also increase the clock cycle time. Okay. So, okay. Yep, there we go. Number of clock cycles. Alright. Let's go. The reason why this is because, as you can see, number of clock cycles is this. And the length of each cycle is this. Many techniques that decrease the number of clock cycles may also increase the clock cycle time. That's why it's a trade-off. Our favorite program runs in 10 seconds on computer A. Okay, this is another quiz type of question. Okay, favorite program runs 10 seconds on computer A, which has a 2 gigahertz clock. We are trying to help a computer designer build a computer B. Trying to help computer designer, which will run this program in 6 seconds. Designers determined that a substantial increase in the clock rate is possible, but this increase will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. What clock rate should we tell the designer to target? Oh, we don't want to see the answer yet. Yeah, this is just math. This is just math. We'll just look at this. CPU execution time equals clock cycles times clock cycle time. So this is number of clock cycles, right? Number of clock cycles. Okay. So when we're improving the performance, the program runs in 10 seconds on computer A. 2 gigahertz clock. Okay, that means that 2 gigahertz seems clock speed, right? Yeah. 2 gigahertz. That's the clock speed. So we don't know, I guess we don't know its we know the wait, doesn't that mean it's 5? 5? Because it's 10. 10 seconds, right? It depends on if this is seconds or not. I don't know what the measurement would be. Because the number of cycles is 5 if that's the case. I think so. Maybe. We'll have to see. We're trying to help a computer design a computer B, which will run this program in 6 seconds. But this designers determined that a substantial increase is possible. Clock rate. An increase of clock rate. Is that good? Causing the computer to require 1.2 times as many clock cycles. It's 5 times 1.2. 6. It requires 6. What clock rate should we tell the designer to target? 6 divided by so we have 6, right? Well, it says it requires 6 clock cycles. Clock rate is 1. Tell the designer to target 1 as clock rate. 1 gigahertz. Let's be precise about our unit. Uh-oh, it's 4 gigahertz. How? What? Oh. What? Clock rate is cycles per second, like that. So it's not based on gigahertz. Bro. Clock rate, yeah, it's 2 billion. 5 over 2 billion. Man. Wait, no. This is X. Well, isn't it just 20 billion? 20 billion cycles. 20 times 1.6. Was it 1.6? 1.2. That's probably, okay, 24. 24 billion is the clock cycles. This is 20 billion. So 24 billion is the cycles that this guy has. Requires 6 cycles. Well, not quite anymore. This would be 24 20 billion. 24 billion is the 1.2 times clock cycles. So clock cycles, that means it's on the bottom. No, it's on the top. So this x, so this divided by x is 6. So what is x here? Wait, this is 6. No, 4. X is 4. Okay. Target 4 gigahertz. Man, I suck at math. Alright, so that's the answer. I didn't know we were doing like cycles per second. Which makes sense. I'm not gonna delete that. Actually, I'll just say I got it wrong. Alright, instruction performance. The performance equations above did not include any reference to the number of instructions needed for the program. Performance equations above did not include any reference to the number of instructions needed for the program. Since the compiler clearly generated instructions to execute, and the computer had to execute the instructions to run the program. Average number of clock cycles per instruction for a program. Average clock cycles per instruction. Okay. So this is the number of clock cycles, right? Clock cycles per instruction. Suppose we have two implementations of the same instruction set architecture. Oh, no. And by how much? Well, the CPU clock cycles equals instructions times average clock cycles per instruction. Clock cycle time, CPI. Well, we have this equation as well. So they gave us CPI, which is this. How many instructions? Clock cycle time. Yeah, clock cycle time is that, right? Number of clock cycles is this. So we don't know the number of instructions, but since it's the same program, we'll have the same number of instructions, right? Whether it be 5 or 6. I don't know, like millions. It's the same program, right? 2 implementations, the same ISA. So if these are the same, does that really matter? Clock cycles? Let's say it's just 1 number of instructions. CPI is 2, so for this one is 2, and then this one is 1.2. So clock cycle is going to be 2, number of clock cycles. 2 times clock cycle time. Okay. 2 times 250 is 500. And 500 times 1.2 is 600. Computer A is faster by 100 PS. Or what's PS? Oh no. Well, let's check the answer. I'm not really sure. Oh. It's probably 1.2, yeah. 1.2 times. Yep, okay. Pretty straightforward. The classic CPU performance equation. This is getting a little bit messy, I'm not gonna lie. Classic CPU performance equation. We now write this basic performance equation in terms of instruction count. The number of instructions. CPI is cycles per instruction, right? Cycles per instruction. Yep. And clock cycle time. CPU time. Instruction count times CPI times clock cycle time. CPU time. Wait, I thought CPU time was, oh, we just inserted that in here, right? Yeah, we did. Or instruction count times CPI over clock rate. These weren't particularly useful because they separate the 3 key factors that affect performance, Instruction count, CPI, and clock rate. You can use these formulas to compare two different implementations or to evaluate a design alternative if we know its impact on these three parameters. Yo, this is so cool. I've never really read about this. I should have always. A compiler designer is trying to decide between two code sequences for a particular computer. Two code sequences. The hardware designers have supplied the following facts. Whoa. The CPI, the what's CPI again? The per instruction, something cycles per instructions. God damn it. Clock cycles per instruction. Yeah, clock cycles per instruction. For a particular high-level language statement, the compiler writer is considering two code sequences that require the following instruction counts. So the sequence 1 requires a instruction counts for each instruction class. So A would be either 2, 4, B would be 1 and 1, B doesn't matter, and then for C it's 2, 1. Which code sequence executes the most instructions? Which will be faster? What is the CPI for each sequence? Alright, we need to answer these three questions. Which code sequence executes the most instructions? Which will be faster? What is the CPI for each sequence? Should probably move this to here. Yep. Whoa, okay. No. How do I normalize this? Alright, I think I'm just gonna delete it. No, copy it. And then, man, how do you do this? There we go. Okay. Code sequence executes the most instructions. So we're concerned primarily with this instruction count. CPI is 1. CPI times instruction count over the clock rate. We don't know the clock rate, right? Would the clock rate always be the same? Clock rate is... Yeah, it would be the same, I think. Oh, yeah. Well, I mean, it's gonna be the same between the instruction, right? Yeah. The clock rate is not provided, though. Yeah. I think I have to assume, like, one of these are given, no? Because I don't really know what to use. What's the other formula that we have? This is instruction count times CPI times clock cycle time. What's the first one? Is that the first one? Number of clock cycles, that's not really produced. That's not given. Alright, let's just assume clock rate is the same for at least like A. Yeah. So if clock rate is 1, instruction count is 2 times CPI is 1, is 2. So A sequence 1 A is going to be 2 times 1 is 2. B is going to be 2 times 1 is 2. And C is going to be 2 times 6, or 3 is 6. Sequence 2. 4, 2, and 3. Six, 4, and 9. C. Wait, instruction count times CPI. Instruction count. Executes the most instructions. Wait, that would just be whatever has the highest number. Yeah, A. A with 6. Which code sequence executes most instructions? I guess we have to add these up. 2, 2, so 10? No. We have to add these, I guess. 3, 4, 5. 6, sequence 2. Which would be faster? Okay. This is the 4 times 10. This is 4, 2, 6, which is 6 plus 3 is 9. Sequence 2. What is the CPI for each sequence? CPI for each sequence. Is that really the question? CPI for each sequence? Wait, what? Isn't it just 1? Maybe we add this up to 3 plus 2 is 5. We have 5 instruction counts times CPI is, I guess we add these up too. I don't know, 6 for sequence 1. 2 is gonna be 6 times 6. I don't know what I'm doing, honestly. 36. Oh my god. Sequence 1 executes 2 plus 1 plus 2, 5 instructions. Right. 4 plus 1 plus 1 is 6. Therefore, sequence 1 executes fewer instructions. Wait, you said most instructions. Can use the equation for CPU's clock cycles based on instruction count and CPI to find the total number of clock cycles for each sequence. Yeah, 10.9 is what I got for this. Yes. Oh, this is wrong. Code sequence 2 is faster, even though it executes 1 extra instruction. Since code sequence 2 takes fewer overall clock cycles but has more instructions, it has lower CPI. The CPI values can be computed. Oh, didn't even realize we can do that. CPI is actually CPU execution time over instruction count. CPU clock cycles. What? Why are we dividing this? Oh, you're using this. What the heck? Oh. Okay. So what's the other equation? So you take this and use this here. CPU execution instruction count times CPI clock rate. All right, how long have I been on this? Okay, so the CPI is instructions. CPU execution. Wait, how the hell did we get to that? CPU clock cycles. Oh wait, this is what is that again? Oh my god, there's so many equations right now. All right, CPU time is this. There's another equation, which is this one. CPU execution time is cycles over clock. So for this, since the CPU clock cycles is this, right? What can we do about that though? What can we do about CPU clock cycles? How does that equation come to be? I need to write it down. This is confusing. This is why I need an iPad. I'm gonna buy one. So the equation we're trying to get is CPI, CPU clock cycles over instruction count. CPU execution time. CPU execution time, CPU clock cycles over clock rate. Mm, Why am I so slow, man? CPU execution time is CPU clock cycles over clock rate. CPU clock cycles is instructions times CPI. I get it. I get why it works. Okay, so how we got to this equation is since instructions times CPI over clock rate is finally got it. It's been a while since I've done math. Right? So instructions times CPI is CPU clock cycles. CPI is CPU clock cycle. No, wait. CPU clock cycles. CPU clock cycles over wait. Instructions. Yeah, instructions. All right. CPU clock cycles for sequence 1. What's the clock cycles? Clock cycle is instructions times CPI. So what is the CPS for each sequence? So I guess you add these up. 6 times the instruction. 212 is 4 plus 5. 4 plus 1 is 5. So it's 30. CPI is 30 over the number of instructions, which is 5. Is it 6? What's the instructions? This is 1 to 3 is 6 times 5, 6 is 36 over instructions. Is that right? It's not right. CPU clock cycles. How do you get CPU clock cycles? CPU clock cycles is CPI times CPI. Oh yeah, 2 plus 2 plus 6. 2 plus 2 plus 6 is 10. Yeah, okay. I did the calculations wrong. 10 over instructions. And this one is going to be 4 plus 2, 6 plus 3 is 9. Wait, is that right? Yeah. The number of instruction is 6. And for this, it's 3, 5. This is 2. This is 3 over half is 1.5. Okay, so what's that? What are you asking? What is CPI for each sequence? Oh, okay, there we go. All right, nice. Basic measurements at different levels in the computer and what is being measured in each case. We can see how these factors are combined to yield execution time measured in seconds per program. Okay, this is the last 2 pages. Basic components of performance and how each is measured. The components of performance. CPU execution time for a program. The instruction count. The CPI and the clock cycle time. Seconds for the program. In instructions executed. Average number of clock cycles. Yep. If we know the clock rate and CPU execution time, we only know, okay, so how to get these values. Clock cycle time is usually published. This is clock cycle time. That's clock rate, right? Clock cycle time. Clock cycle time. Clock cycle time. Is that clock rate? Let me double check. Yeah, it is. It's the inverse of clock. Yeah, that makes sense. Because we had that Microsoft example. Dude, that example video is so goated for this. So goated. Like example, Windows had 3 point something gigahertz. CPU execution time from running the program. We need to determine either the clock rate and instruction count. Measure the instruction count by using software tools. That is cool. We don't need to know the exact details of the implementation to get the instruction count. The CPI depends on a wide variety. Including the memory system and processor structure, as well as the mix of instruction types executed in an application. Thus, CPI varies by applications as well as among implementations with the same instruction set. The above examples shows the danger of using one factor to assess performance. When comparing two computers, you must look at all three components, which combine to form execution time. If some of the factors are identical, performance can be determined by comparing all the non-identical factors. Since CPI varies by instruction mix, both instruction count and CPI must be compared, even if clock rates are identical. Measure of the dynamic frequency of instructions across one or many programs. Okay, several exercises at the end of this chapter ask you to evaluate a series of computer and compiler enhancements that affect clock rate, CPI, instruction count. Common performance measurement that does not incorporate all the terms but can be misleading. The performance of a program depends on the algorithm, the language, the compiler architecture, and the actual hardware. The following table summarizes how these components affect the factors in the CPU performance equation. The algorithm, programming language, compiler, ISA. Well, the algorithm determines how many instructions that we will have, the cycles per instruction as well, right? Yeah, hence the number of processor instructions executed. The algorithm may also affect the CPI by favoring slower or faster instructions. For example, if the algorithm uses more floating point operations, it will tend to have a higher CPI. Wow. Wow, I did not know that. So, I mean, that makes sense. Well, that doesn't really make sense right now, but I think I can see why. It's because I actually don't. Maybe we'll figure out later. The programming language certainly affects the instruction count, since statements in the language are translated to processor instructions, which determine instruction count. Language may also affect CPI because of its features. Yeah. Well, that makes sense. Efficiency of the compiler, the average cycles per instruction, since the compiler determines the translation of the source language instructions. Yeah, the compiler will, yeah. The ISA affects all three aspects of CPU performance, since it affects the instructions needed for a function, the cost of cycles, and the overclock rate for the processor. Damn. Alright, this is check yourself. Okay. I will do this probably tomorrow. I think I'm done for tonight. It's 10 p.m. But yeah, I think I'm done with 1.4. I've done a lot of the quizzes. Yeah, my notes are very messy now. It's okay. We can clean up later when we review 1.4. Alright, so today, I have to finish this quiz. I guess I'll start tomorrow by doing this, because I do have to read the Bible a little bit today. I kind of promised myself I'll read a little bit of Bible every day. And yeah, I cannot just not do that. So yeah, today was a good day actually. Didn't really think we would finish 1.4, but we did. Really nice. This was a tough chapter, not gonna lie. This was a tough chapter for me. Next chapter we read is gonna be, what's day 3? Um, we are gonna move on to the power wall. Is that the last of chapter 1? Yeah. I really want to learn cache memory. This is very exciting to me. What's chapter 2? So chapter 1.5 is power wall, the switch from uniprocessors to multiprocessors. Wait, is that what you said it's gonna be? Switches to multiprocessor. Oh yeah, it is. Yeah, I mean these are not really useful, I guess. Language of the compiler. The assembly, right? Alright. Yeah, this is exciting. We only have 7 chapters. We actually only have 7 chapters. This might go faster than I thought. So we're already on 1.5. Let's go. Okay, good progress today. Bye bye, guys.